All right. Good afternoon again, everybody. So I think we can start. I just started the recording so that for those who will come in late today, they can just rewatch the first parts of the discussion. But just a quick recap. So due to the transport strike earlier this week, all of the undergraduate instruction were moved to online asynchronous mode. That's why last time I really didn't have the time to meet you from 5:30 to 7 live. So I have to record other classes for my record some videos for my undergraduate classes this semester. So yeah, I hope you got the time to watch the recording already, because for today I'll just continue the discussion and finish off the discussion of the module on LU factorization. But before proceeding, do you guys have any questions aside from that silly arithmetical mistake I committed during the discussion? It's a problem of recording things, right? So even if you're not sure, I cannot hit pause and then double check myself first, because that will be time consuming video editing the video. But anyway, do you guys have any questions? I guess that video covered Gaussian elimination and how it is done by hand. And then I think I alluded to a way of harvesting the LU factorization out of the Gaussian elimination or the Gauss-Jordan algorithm, right? So the key is you start with a matrix A. In my example, or in my discussion, it was a square matrix A. We perform elementary row operations to it and reduce it to an upper triangular matrix. The beauty behind that process is that performing elementary row operations does not change the solutions to the system. In short, we are getting an equivalent system from the matrix A. So again, if you have the matrix equation AX equals B, you perform elementary row operations and you transform A into an upper triangular matrix. Then the solution that you get is still the solution that you will get from the system involving the matrix A will still be the same as the solution that you will get by solving the matrix equation involving the matrix U. But in this case, U is an upper triangular matrix. And so if you have an upper triangular matrix, again, it's a matrix where all the entries below the main diagonal are all equal to 0, then you can perform back substitution easily, right? Without matrix inversion and all of those very computationally expensive processes, then you get the solutions more efficiently or more accurately, especially if you're performing it using a computer or using a machine. So yeah, so you get a solution using back substitution, and well, that's very useful. That's one that's one efficient way of solving systems. The cost of the computations there is just a factor of n cubed, or proportional to a factor of n cubed. That's what we mean by that's what we meant when we say big O of n cubed, right? So the number of operations grow proportional to n cubed, or almost proportional. The correct term is asymptotically proportional to n cubed, where n is the number of rows or columns, right? It is still expensive, but that's the most efficient that we get, right? And again, the problem we're solving here is computing large systems, or solving for large systems repetitively or iteratively, right? Now, the Gaussian elimination process will give rise to an LU factorization of the matrix A. Again, the matrix A will then be written as a product of a lower triangular matrix L and an upper triangular matrix U. And the LU factorization is very helpful if you want to solve the same system over and over again. When I say same system, with the same coefficient matrix A, but a different right-hand side vector B. So that's where LU factorization or any matrix factorization method will prove to be more efficient than just plain old matrix inversion. All right. So yeah, going back to my question earlier, do you have any questions about the factorization method? Actually, did we go? Yeah, I think we discussed the gist of the matrix factorization, but you might realize that it still seems to be a very expensive process, right? Because I guess we stop here with this paragraph over here telling us how to get the LU factorization of a matrix A. Again, you perform Gaussian elimination, either using elementary row operations or multiplication of elementary matrices. We'll get the matrix U, all right? But the matrix L is found by multiplying the elementary matrices corresponding to the elementary row operations, actually not just the elementary matrices, but the inverses of the elementary matrices, right? So we need to multiply E1 inverse by E2 inverse until E sub M inverse just to get the matrix L. And that's still a very tedious process, right? Now, I promise, I guess, towards the end of the video that we will have a shortcut in determining or in assembling the matrix L, because the matrix U is simply the result of our plain old Gaussian elimination. So the challenge is building up the matrix L. All right. Now, let's see. Sorry, I have a cup of coffee with me, so I'll pause from time to time to sip some coffee. But anyway, so let's see. What is that shortcut I'm alluding to? Well, I think that's here. After exercise 7.4, I mentioned here that the bulk is really on computing the matrix L. Now, we can do so, or we can find the matrix L more easily by just taking note of the scaling factors we use for the row translators, right? So for instance, if you perform the elementary row operation R sub I being replaced by R sub I minus C sub R sub J, you just take note of the value of C, the scalar multiplier C. You call that Mij. That's going to be the entry on the ith row and the jth row of the matrix L. Again, so you have, because here in the factorization we're developing, right? So we have the diagonal, the main diagonal of the matrix L to be comprised of all ones, right? It's lower triangular, so everything above the main diagonal should be a 0, right? So all that's left to be determined are the entries in the lower triangular part, right? And that's what we will get if we will perform the multiplication of the inverses of the elementary matrices over here. But again, that's a very tedious process, right? Now, this method just tells us that, or this remark over here, this paragraph here is telling us that the entry on the ith row and the jth column of the lower triangular matrix L will be the constant multiplier, all right, of the scaling constant negative C. That, or actually, let me rephrase that. The entry on the ith row and jth column of the lower triangular matrix L is essentially the multiplier negative C, all right, or the the multiplier C that we use to scale the matrix, the row J that was used to translate the ith row, right? So basically, you look for the elementary row operation corresponding to changing the ith row by scaling it by the jth row, and take note of the multiplier negative C you used for the jth row, right? So maybe it's easier if we look at it from an application point of view, all right? Or let's see. Let me go back to that example where we wrote, the elementary operations. So so let's look at this particular example. So this is example 7.4. So I have here the Gauss-Jordan algorithm for the matrix A, and we eventually got this upper triangular matrix U. So this will be the U in our LU factorization. But again, we can find the matrix L by simply taking note of the multipliers. Let me put it a little bit down, all right? By taking note of the multipliers to the row translators, All right. Now, again, it's a lower triangular matrix. In our LU factorization scheme right now, all the diagonal entries are all ones. So this is a 4x4 matrix. So L will also be 4x4. All entries above the main diagonal will all be zeros. And then the lower triangular or the lower entries, right, over here will be the multipliers to the row translators, right? So for instance, you look at this elementary row operation. This translates the second row by a multiple of the first row. So that means this multiplier, 3/4, right? Because the form that I have in the remark earlier is Ri being replaced by Ri minus C R sub j. And I'm looking for the value of C, right? So if you compare this form with this guy, that means I is equal to 2, J is equal to 1. So that means the multiplier C, which in this case is 3/4, would be the entry on the second row, first column of the lower triangular matrix L, right? So that means this must be a negative, this will be 3/4. Okay. Now, moving on, we are translating the third row by a multiple of the first row. That means the multiplier C here, which is 1/2, will be what? This will be the entry on the third row first column, right? So there would be a 1/2 over there. So you see, we are assembling the matrix L little by little by looking at the uh, the the elementary row operations that we perform, right? So essentially, I am hiding behind this seemingly lexicographic assembling of the matrix L, the multiplication of the inverses of the elementary matrices, all right? Then if you continue the pattern, I'll know that the entry on the fourth row, first column, will be 1/4. So this will be 1/4. And then here, let's see, 3/2 will be 6/7 coming from here. And then the entry on 4/2, fourth row, second column, will be 5/7. And then lastly here, I'll have 5/6. That would be the entry on the fourth row, third column. So that would be 5/6. So this is our L. This will be our U. If you multiply them together, but L is on the left, U is on the right, you're going to get the matrix A again, right? You can do the same thing and double check your understanding of that process by looking at, I think we had an earlier example than this. Let me see. Uh-huh. Oh, yeah, I think I did it towards the end of the lecture last time. The one involving the matrix 2, 5, 3, 3, 1, -2, and -1, 2, 1. All right. But again, there's still one problem with this method. You really need to perform the elementary operations, right? But essentially, if you do this, you only need to do this once. Whenever solving equations involving the matrix A. You don't have to redo the Gaussian elimination. You can just store the matrix L, the matrix U, and use that to solve any system. Any system. You have a system with the same coefficient matrix, but a different right-hand side vector, right? Now, let's look at a particular example of how this can be very useful. Oh, by the way, we can let's try it another time. Example 7.5. So this is the example I was supposed to do. Not the other one, but anyway, that's the beauty of doing it live. You find alternative examples, right? So yeah. So in example 7.5, performing a Gaussian elimination or the Gauss-Jordan algorithm, it'll get the matrix U over here. That's our upper triangular matrix. Now, the lower triangular matrix can be computed in the same way as the example did, multiplying all those elementary matrices. But I don't want to do that. I want to save some time or some computational resources. Rather than multiplying matrices, I'll just do the lexicographic assembling of the matrix L. Now again, matrix L, all ones on the diagonal, zeros on all entries above the main diagonal. Now, entry on the second row, first column, will be the multiplier over here. So I'll have 3 over 2. And then third row, first column, I have a plus 1/2 here. I need to reverse the sign. So this will be negative 1/2. And on the third row, second column, I have a plus 9 over 13. So here I'll have a minus 9 over 13. And that's going to be our matrix L. And hopefully this is the same one as the one below. It should be the same one as the one below. There we go. Right. So that means the matrix L and the matrix U can simultaneously be found by performing one pass of the Gauss-Jordan algorithm, right? So you don't need to insert some additional matrix multiplications. All you need to do is, again, take note of the multipliers to the row translators, getting their negatives and assembling them to get the matrix L, right? So is the process clear? Or do you guys have any questions? Yeah, Z.
Sir, question po, is the LU decomposition unique for any matrix A?
Good question. It is not unique. I'll show you another LU decomposition later, right? Okay, other questions? Okay, so if there are none, so maybe you were intrigued about the use of or how LU factorization can be used to efficiently carry out solving many systems with the same coefficient matrices iteratively, right? Now, I guess that's the next subtopic that I will discuss before addressing Z's question about the uniqueness of the LU factorization, right? Now, imagine you have the matrix equation AX equals B, right? Oh, by the way, my notations in this module is curly M sub n by 1. That means that's a matrix with n rows and 1 column with entries comprising of real numbers, right? So that's if I have a curly M, then an M by n below, then C over here. This is the set of all matrices with M rows and n columns and whose entries are complex numbers, right? But from time to time, I'll shift from real entries to complex entries, but the algebra is still the same, right? Okay. Now, if you have an if you have an n by n matrix A, all right, and then you have an n by 1 constant matrix B, and again, the main problem we had is when the matrix B changes over time, right? And we have no way of finding the matrix, the vectors B all at the same time. So we cannot do a generalization of the Gaussian elimination process. That's why we need to perform the computations iteratively, all right, or one after the other in series rather than doing everything in parallel. Now, you consider the matrix system AX equals B. And again, if you were able to find an LU decomposition for the matrix A, then we simply replace A by the product L times U. And again, be careful with the ordering of the multiplication because matrix multiplication is not commutative, right? So L times U is different from U times L. So you need to be a little careful about the ordering, okay? Now, but the nice thing, even though matrix multiplication is not commutative, it is associative. So we can alter the grouping of matrix multiplication, all right? And that's what was done in the next step, right? Instead of multiplying L and U together first, before multiplying it with a vector of unknowns, X, right? So I'll multiply U and X together first before post multiplying the product to the matrix L, right? So I simply translated the parentheses one step to the right. Okay, I didn't alter the ordering of the matrices. L is still the leftmost, followed by U, then followed by X. In this particular grouping, L is still on the leftmost, U is in the middle, and X is in the right. Right? So that's still fine, and then that's still equal to B. So I'm still following the rules of linear algebra over here. And the trick here is to let Y be equal to U of X. So we are just changing the variable. Instead of the unknown the unknown vector is X, I'll replace it by the product UX. And anyway, that's still well defined, right? So if A is n by n, right? In the LU factorization, you will still get two n by n matrices. N by n, n by n. So U is n by n, X is n by 1. So still the product is n by 1, right? So this statement is still valid, right? But with that change of variable from the unknown variable X to the unknown variable Y obtained by multiplying U and X, we get a new linear system. We'll have Ly equals B, right? So essentially you have your lower triangular matrix L times your new variables Y1, Y2 until Y sub n equals your vector B1, B2 until Bn. Okay? Now, the nice thing about this is that the matrix L is lower triangular. If it's a lower triangular matrix, then you can do forward substitution, right? No need for matrix inversion, which I keep on telling you over and over again. It's a very expensive and a very numerically unstable process, right? So you only need to do forward substitution. So you can solve for Y1 or the value of Y1, follow, and then use the result to solve for Y2, and then use Y1 and Y2 to get Y3 until you determine the values of all the Ys. Okay, but what you computed from this forward substitution are the Ys. But remember, our original variables are the X sub I's, right? So, but we know that Y is equal to UX, the original variable. So you can just plug that value in. Remember the substitution step we did earlier? We just need to revert to the original variable. So we'll have the matrix U, which we know from the LU decomposition. And then we'll have X1, X2, until Xn, our original variables, equals the value of the Ys that we found from the forward substitution. This is the second equation, or the second system of equations that we want to solve. But again, this is not a big deal because U is upper triangular. It's upper triangular, so we can solve the current system by performing back substitution. So we can go from the bottom up, right? So since this is upper triangular, the last row would be comprised of all zeros except the last entry. That's not equal to 1, but that should be UNN, right? Back substitution. So you'll get the value of X sub n. Then you can use the value of X sub n to retrieve X sub n minus 1 all the way up to X sub 1, right? But again, here, you will use the values of the Y that you got from the previous step. So now, if you know that you have if you know the coefficient matrix A, all right, all you need to do is to get the LU factorization using whatever method you want. You can use the method that we discussed starting last Tuesday, and then store that in your memory. And then once the data that will comprise the vector of constants B, you can just retrieve the lower triangular matrix, perform forward substitution to get the values of the Y sub I's, and then after that, retrieve the matrix U from memory, and then use back substitution. But this time, your right-hand side will be the Y values that you got from before. Okay? So that's the entire process. So essentially, instead of inverting the matrix A, we will use a combo of a forward substitution plus a back substitution that is hinged on an LU factorization. This is highly numerically stable, and this is very cost efficient in terms of computational expense because all you need to have is L and U, which can be stored in memory. Okay. So let's take a look at a quick example how this process will pan out with specific matrices. All right. Now in example 7.6, I have the matrix system given in equation 7.7. Here's my coefficient matrix, and this is my right-hand side vector. All right. Now, again, you can interpret it as finding the best parameters. Say you are modeling something, and then you have 4 parameters. Say, just for the sake of example, maybe you have your birth rate, mortality rate, immigration rate. So if it's about population dynamics, then what else? Maybe the carrying capacity of, say, your province. So you are modeling the population dynamics in a certain province or a certain locality, and you want to get an estimate for the birth rate, mortality rate, immigration rate, and carrying capacity by using a stratified sampling of the population. But for instance, for whatever reason, you were able to find out the relationship between the birth rate, the mortality rate, the immigration rate, and the carrying capacity to be defined by the coefficient matrix A. All right. So this is extremely helpful if you are, say, aggregating the results from small localities to the other. So from local communities up to a larger community. So for instance, in District 1 of your province, you found out due to experiments, data analysis, and so on, you found out that twice the birth rate minus thrice the mortality rate plus the immigration rate plus twice the carrying capacity will give you a score equal to 2, whatever that score is, right? But if you go to District 2, the relationship is as follows. 5 times the birth rate minus mortality rate plus twice the immigration rate plus the carrying capacity will yielded a score of -3 for that particular district, okay? And so on. So you have 4 districts for your data. And then you want to estimate, though this is not the ideal way to do it, right? But at least one way of doing it is to aggregate those results and find what is the birth rate, the mortality rate, the immigration rate, and the carrying capacity on the aggregate of those districts, right? Now, of course, you can just find A inverse and then multiply it to B, but that will be very costly. In this particular example, it is not that very costly or unstable because we only have a 4x4 system. But if you have 100,000 by 50 matrix, that would be that will be impossible, right? Because it's not a square matrix. But even if your matrix is square and it's invertible, matrix inversion, again, is a very expensive process, and we want to avoid that at all cost. And then I'm also looking forward to using the same coefficient matrix to solve a different system or a system with a different right-hand side. Maybe the dynamics or the relationship between these four parameters varies through time and will give you a different score for the same district. So that's also possible. And you don't want to redo all the computations again. So you can just retrieve your LU decomposition and then do the forward and backward substitution. All right. So yeah, let's see how this is done. So you do the LU factorization. You will get this 2 matrices. And again, following the procedure laid down earlier, so we first solve, we let y equals ux. And then again, you have ax equals b. Then we can have L times u times x equals b. And then associative laws will apply. So we'll have that. And then we will call ux y. So we'll have ly equals b. That's what is solved here. All right. And then expressing this in expanded form, we'll have our lower triangular matrix L over there times the matrix y1, the vector y1 until, sorry, this should be y sub 4. Okay. And then here you can do forward substitution, right? If you multiply the first row by the first column, you'll get y1, that's equal to 2, right? And then multiply this guy by this guy, you get the dot product, right? So the dot product would be 5 halves of y1 plus y2. You'll have a bunch of zeros for y3 and y4, so they will just be out of the equation here, and it's going to be equal to -3, right? So here you have one equation with 2 unknowns initially, but take note that we already found the value of y1, so you can just plug it in here. So you can replace y1 by 2, so you'll get this, y2 equals 8. So you now have the value of y1 and y2. You can use that for your in your third equation. The third equation is found by multiplying third row by your unknown vector, or the vector of unknowns. So you're going to have 3 halves y1 plus y2 plus y3 equals what? This should be equal to 5. There should be no subscript over there. Okay. And then use the values of y1 and y2 that you found before. And eventually, using simple algebra, you're gonna get the value of y3. I guess I knew what was the typo here. This should have implies y3 equals 10. Okay. And then again, you can continue the process, and then you'll get y4 equals 6 over 13. Okay. But the work is not yet done, because all you found out here are the values of the y sub i's, right? But our unknowns are the x sub i's. But it's very important, so you harvest the values of y into your vector, or into a vector y. So 2, -8, 10, and 6 over 13. And then remember that ux is equal to y. So you retrieve your upper triangular matrix U, and then expand the vector of unknowns for the x's. So you have x1, x2, x3 until x4 equals the value of y. And then from here, you can perform back substitution. Actually, I guess there is another typo. It should be a 0 over here. Okay. And then you perform back substitution. So you get 71 over 3 times x4 equals 6 over 13. You solve for x4, you'll get this guy. And now I'm doubting this answer. So I have 71 over 3 times x4. That's equal to 6 over 13. So that means x4 must be equal to 6 over 13 times 3 over 71. So this should be 6 over, why 6 over 71? Unless there's a typo again here. Yeah, I should have given you my handwritten notes, because I asked my intern to put this note into LaTeX, so I haven't checked it yet. But yeah, but this should be 13, 6 over 13. Huh. So I'll need to double check this, but I hope the process is clear. So you do the back substitution, you start from finding x4, use that value to get x3, and then use x3 and x4 to get x2 all the way up to x1. Okay. Is that clear? Any questions? I'll just need to double check my the arithmetic there. I started to doubt all these numbers over here. Okay. Now, if that is clear, one possible problem set that I could give you is to to use this method or this LU factorization, assuming that the numbers are all correct, to solve another system of equation, the same matrix A, right? The same coefficient matrix A, but with a different right-hand side B, right? This should be 1, not capital T. Okay, lesson here. I'll just give you my handwritten notes rather than the latex one, right? Okay. So that you experience firsthand the the advantage of using LU factorization over matrix inversion or Gaussian elimination, right? Because you can use the LU factorization repetitively, right? Even if you don't know even if you don't know the right-hand side vectors all at the same time. Okay. Right. So going back to Z's question earlier, is the LU factorization unique? Actually, it is not. Actually, the LU factorization that is tackled here will not always exist in the first place. So not just a question of uniqueness, but also of existence. Because there are some nice matrices that doesn't allow or that doesn't admit an LU factorization using only row translations, because the method that I illustrated here only works if you can perform the LU factorization without the use of permutation matrices. All right, because as you have seen in the examples, only row translations were used. We are not interchanging or swapping rows. Swapping rows will require not an LU factorization, but you will have a preconditioned LU factorization. So for instance, you have the matrix A over here, 0, 1, 1, 0, right? Now, this matrix doesn't have an LU factorization without row interchanges, right? Because if I can write this, or the proof of the non-existence of an LU factorization for the matrix A is as follows. So it's a proof, what we call in math as a proof by contradiction. So suppose for the sake of contradiction that there exists an LU factorization for the matrix A without row interchanges, right? So if there's an LU factorization, then that factorization will look like this, right? So I have a lower triangular matrix L and an upper triangular matrix U. Okay, just for the sake of contradiction, I am assuming that there is an LU factorization, right? So if there's an LU factorization, that should look like this, right? But what is implied by this factorization? Well, if I multiply this first row by the second column, I'll get what? I'll get L11 times U12, right? And that will be equal to this entry, the entry on the second column, first row. So that will be equal to 1. So L11 times U12 should be equal to 1 if this factorization is true, right? So that means L11 and U12 are both non-zero, right? Because if one of them is equal to 0, then we cannot get a product equal to 1. L11 times U12 is non-zero, so both of them are non-zero, right? Now, again, assuming that this is the right factorization, then I can multiply the second row by the first column to get the entry on the second row first column, right? So I'm going to have L21 times U11 equal to 1. And again, I get a non-zero product, so neither L21 nor U11 is equal to 0. Hence this conclusion, right? However, if I check this, if I multiply this guy by this guy, I'll get what? I'll get L11 times U11, and that should be equal to what number? That should be equal to the number on the first row, first column, right? So that means L11 times U11 must be equal to 0, okay? And that's what is written over here, right? Now remember, when can we get a zero product? So we can only get a zero product when either L11 or U11 is equal to 0. So this statement over here means that at least one between L11 and U11 is equal to 0. But we already concluded before that L11 is not 0 and U11 is not equal to 0. Hence, we get a contradiction, right? So that means this factorization cannot happen. Right? So that means the matrix 0, 1, 1, 0 doesn't admit an LU factorization. Okay. But if we do the row interchange, so here if I interchange row 1 and row 2, I'm going to get 1, 0, 0, 1, which is the identity matrix. But this guy is just 1, 0, 0, 1 times 1, 1, 0, 0. Identity times itself. This is lower triangular. This is upper triangular. Right? But this is not the matrix A. This is the matrix A times a permutation matrix times the matrix with the identity matrix, first row and first and second rows interchange. So this is 0, 1 times 1, 0, right? So we get an LU factorization, but not for the matrix A, but the matrix A prim multiplied by an elementary matrix. Actually, this is what we call a permutation matrix, because it is the identity matrix with some of its rows interchanged. So essentially, for this example, I don't have an LU factorization, but I have an LU factorization of P times A. So this is a preconditioned LU factorization, right? Preconditioned because we are multiplying the original matrix A by a preconditioner. It's preconditioner because it appears to the left. It's a multiplier to the left, right? So we need to precondition the matrix A before performing the LU factorization. Okay. Now this is still valid, right? Because the solution in for this system is equivalent to the solution for the system AX equals B. But again, there's an additional step, the preconditioning of the matrix A, right? But for most applications, preconditioning are handled during pre-processing before we perform the entire matrix scheme to the system, right? That's why usually, unless it's a numerical linear algebra course, I do not discuss preconditioned operations in details, right? But so that you know, not all matrices have LU factorizations. Okay. Now, when can we be assured that a matrix can be LU factorized? All right. I have a theorem 7.4 for that. Now, not all non-singular matrices or not all invertible matrices have LU factorizations. Actually, a non-singular matrix A will have an LU factorization if and only if all of its leading principal minors are all 0, right? Now, what do I mean leading principal minors? So if you have the matrix A comprised of A11, A12, A13, until A1n, let's consider an arbitrary n by n matrix. We'll have A21, A22, A23, until A2n, and so on, all the way to AN1, AN2, AN3, until A3n, all right? The principal minors are the determinants of the submatrices starting from the upper left-hand corner. So the first minor is A11, a 1-by-1 matrix starting from the upper left corner, right? So A11 is the first minor, or the absolute value of that will be your first minor. And then the second minor is the 2 by 2 matrix starting from the upper right-hand corner, right? So you compute for the determinant of A11, A12, A21, A22. That's the second minor. The third minor is the 3 by 3 matrix starting from the upper right-hand corner, or sorry, upper left-hand corner. So that's the determinant of this 3 by 3 matrix. You compute it, and then you continue the process. So you're just increasing it one column and one row at a time until you get the entire matrix. So you will compute all the minors or all the determinants of these upper left-hand submatrices. And if all of those principal minors are non-zero, then you will have an LU factorization. And it's an if and only if statement, so it's a characterization of all the matrices, all the invertible matrices that can be LU factorized, right? So I'll not be giving the proof, nor will I give an example of it because it's a very costly process, right? Because if you have a 100 by 100 matrix, you need to compute 100 determinants. And computing determinants is also a very expensive task. But just, so that you know, there's a way to guarantee the existence of an LU factorization. Yes, Christian, you have a question?
Yeah, sir. So we found here that doing the LU factorization is expensive, but at the same time, figuring out if it can be factorized is also expensive. So is it worthwhile checking the existence or just letting the computer run it and figure out if an error will come out later on?
Yeah, good point, Christian. Yes, it's very expensive to compute to check whether the matrix can be LU factorized. Computing the LU factorization is not that expensive. It's just big O of n cube, but you're right. Checking if it's a factor, if we can factor it using an LU form, is very expensive. It's a very tedious task. So you're right. What we can just do, we write the program, or we use a program or a software for the LU factorization in any way. If it's not LU factorizable, then there would be an error. There would be a division by zero that will occur if you ask a computer to do the LU factorization. So you can spot it right away. So that's why I don't want to give an example of the utility of theorem 7.4. Theoretically, it's a nice result, but if you look at it pragmatically from the applied math point of view, it's not that important. But theoretically, it has lots of nice implications. But of course, we're not here after the theory, we're after the utility of these results, right? Okay, so we now have an idea when the LU factorization of a matrix will exist. Now, the nice question Z posted earlier, will it be unique? It won't be unique, right? So if you guarantee the existence, you don't know about uniqueness, right? Now, the method that we described earlier, or that we performed earlier, gives us the following form. So you have an upper triangular matrix U, okay? So U11, U22, until UNN. And then upper triangular, so everything below the main diagonals are zero. You have a bunch of entries over here. We don't know how they look like. The process will give us those coefficients. And the lower triangular matrix that we will get from the factorization that we discussed will be a unit lower triangular matrix. All the diagonal entries would be 1. It's lower triangular, so all entries above should be 0. And then we'll have a bunch of numbers here, which will be coming from the multipliers to the row translators, right? So that's how we get the factorization. Now, this is what we call the Doolittle form, or the Doolittle LU factorization of the matrix A. Yeah, I wrote that over here. So that's the Doolittle factorization. So if you go to this matrix, 1, 4, 3, 2, 7, 9, 5A, -2, The LU factorization using Doolittle's form is this guy. Okay. However, it can easily be verified that this is another LU factorization of the matrix A. Again, it's quite easy because you just need to multiply or carry out the multiplication. You will retrieve the matrix A. And if you look at its form, it is lower triangular. This is upper triangular. How different is this from the Doolittle form? Well, we have a unit upper triangular. We have ones in the main diagonal of the upper triangular matrix. That makes this a unit upper triangular matrix. Well, this guy has non-unit diagonal entries, right? So this is what we call the Kraut factorization, the Kraut LU factorization. So at least now we found two different factorizations of, or two different LU factorizations of the matrix A. We have Doolittle's form, wherein we have a unit lower triangular matrix times an upper triangular matrix. But in Kraut's factorization, we get a lower triangular matrix times a unit upper triangular matrix. Okay. Now, in the module, I also presented a way of performing the Kraut factorization, but it's a little different in how I develop Doolittle's form, right? I did that so that you'll get different tastes of how to derive the LU factorization. Doolittle's form, or the way I discuss Doolittle's form, takes advantage of your linear algebra knowledge, right? Of the Gauss-Jordan elimination process, or if you didn't, if you haven't taken any linear algebra class, that's basically your Gauss elimination procedure, right? But you can attack the Doolittle derivation by using plain old direct factorization and then solving for unknown parameters. That's what I'll illustrate you for the Kraut factorization method. And you can adapt the derivation that I'll be using for the Kraut factorization to get an alternative and more programming friendly form for Doolittle's factorization. Because the way I discuss Doolittle's form is a little bit more on the theoretical side, taking advantage of, again, linear algebra. But the way I will discuss Kraut factorization is more on the programming side, because this is straightforward to be programmed. All right. Now, how can we derive Kraut's factorization? Well, I start with the matrix A, all right, comprising of real numbers as its entries. So this is my matrix A, and I want to write it as a product of a lower triangular matrix L and the unit upper triangular matrix U. So it's a unit upper triangular matrix, so all diagonal entries in the upper triangular matrix are all ones. There's a typo here. There should be a curly L, all right? Now, we can derive all the entries of L and U in the following fashion, right? First, I'll take advantage of the fact that the first column of the matrix U has only one as non-zero entry. So taking advantage of it, I can multiply first row by first column, and that will give me the entry on the first row, first column, right? If this factorization is correct, multiplying this row, this column by this row, or sorry, it's the other way around. Yeah, I'll multiply this row by this column, right? The column of just a 1 and the rest are zeros. I'll get A11, right? But the product is L11 times 1. That's equal to A11. So we'll be able to find the value of L11. Right? Essentially, L11 is just A11. Okay. And then let's do this for all the rows of the matrix L. I'll multiply the second row of L by the first column of U. And what will I get there? I'll get L21, right? Because all the entries after the 1 in U are all zeros. And that will be equal to the entry on the second row, first column of the matrix A. So it's going to be A to 1. So that means L to 1 is just equal to A to 1. So I'll be able to know this. And then you can carry on the process. All the rows will be multiplied by the first column. That will give us all the L sub I once, right? So I'll be able to retrieve all the values of the first column of the matrix L. And incidentally, all these will just be an exact copy of the first column of the matrix A. Agree? Right? I hope you see the pattern. Okay. Only Joshua reacted, so I hope the others, okay, yeah. Alex also reacted. Okay, good. Now, once I figured out what the values of the L sub I once are, I can now proceed by taking advantage of that idea, right? So what I'll do now, I want to retrieve the values of the first row of the matrix U. And I'll do that by multiplying the first row to all of the columns. Okay. So why will that be helpful? Because L11 has a bunch of zeros following it, all right? So that, but I already know what L11 is, so I can figure out what the value of these entries are. So in particular, I'll multiply this row by the second column. I'll get what? I'll get L11 times U12. Since I multiplied the first row by the second column, I will get A12, right? But I already computed L11. So that means U12 is just equal to A12 over L11. And I'm sure that this product, this quotient is well defined because L11 is not equal to 0. Do you remember, guys, why am I sure that L11 is not equal to 0? Let me see if you remembered. Why am I sure that L11 is not equal to 0? Because if L11 is equal to 0, then my computing device, my calculator will complain. Why am I asking it to divide A12 by 0, right? That would be undefined. But why am I sure that L11 is not equal to 0?
Lower triangular.
Yeah, it's lower triangular, but being lower triangular does not require the diagonal entries to be non-zero. Remember, the only requirement for a lower triangular matrix is that all of the entries above the main diagonal are all equal to 0, right? L11 sits in the main diagonal, so we are not constrained to having a non-zero entry there. But good try, Jan. Right? So it's just a technicality about the definition of lower triangular. But why am I sure that L11 is not equal to 0? Otherwise, this method will fail, right? Because my general formula over here is always dividing by L11. Any other guesses? Why am I sure that L11 is not equal to 0? Okay, clue. Look at it another way. L11 is equal to what in terms of the matrix A? L11 is equal to A11, right? Because we mentioned the first column of the matrix L is an exact copy of the first column of the matrix A, right? So why am I sure that L11 is not equal to 0? That's the same thing as asking, why am I sure that A11 is not equal to 0? You guys already forgot? Remember theorem 7.4? I saw Lynette trying to unmute herself. Go, Lynette.
Yes, sir. I was about to say theorem 7.4 as well.
Yeah, what about it?
Yeah, since A11 is also the value of the leading principal minor, and by that theorem, it has to be a non-zero value. So that's why, sir, that L11 should not be equal to 0.
All right, perfect. Thank you, Lynette. Yeah, that's right. We're sure that A11 is non-zero because that constitutes the first minor of the matrix A. And we mentioned that the LU factorization will only exist if the principal minors are all non-zero. A11 being the principal or one of the principal minors should not be equal to 0. All right. So that's a little bit, that's why I'm telling earlier that we don't need to perform the checks per theorem 7.4, right? Because it will manifest itself in a calculation process. So if there's a division by 0, of course, your program will give you a warning or an error message. Then you will know that there is no LU factorization. All right. Now, again, you carry on the process. First row times the third column, you multiply them. The answer should be equal to A13, right? And then the product of the first row and the third column is L11 times U13. We already know L11 to be non-zero. So that means U13 is equal to A13 over L11, right? And that will happen for all the entries in the first row of the upper triangular matrix U, all right? So essentially, that procedure is summarized in equation 7.10 and 7.11. So if you're programming the crowd factorization, you can just include these two guys in a for loop, right? So you're gonna get the values of L of the first column of L and the first row of the matrix U, all right? And then from there, we can successively find the values of the second column of L. So I mean, we need to determine this guys followed by this guys. And then this guys followed by this guys until we reach or until we determine all the entries. Well, how? So to get the the entries on the second column of the matrix L, what I'll do is to multiply all the corresponding rows by the second column of the matrix U. All right. So why will that be helpful? So I'll do this times this. Okay. So second row by second column. Second row by second column will give me A22, right? And the product is equal to L21 times U12 plus L22, right? But the thing is, I already know what L21 is from previous calculations. I already know what U12 is because that's in the first row of matrix U. A22 is given, so that's fine. So we can easily compute for L22, right? L22 will be A22 minus L21 times U12, right? And so on. So to get the value of U, so this will be known, L22. Now to know the value of L32, the one over here, oops. So L32, right? All I need to do is to multiply the third row by the second column, all right? So that will give me L32 and so on. So doing that, multiplying all the rows of matrix L by the second column of the matrix U will reveal all the values of the L sub I2s, okay? And then after that, you can find the values of the second row. I don't know what happened to the highlights that I did earlier. So we already know this. To determine this, guys, the value of U23, U24 until U2n, what we need to do is to multiply the second row by the corresponding columns, right? And then in general, here are the formulas that you need to follow. Okay. And then here you see that the formula for U sub kj involves a division by LKK, which would be the entries here, the diagonal entries of the matrix L. Well, if there is no LU factorization, meaning if the conditions of theorem 7.4 were violated, then LKK is possibly equal to 0, right? And that will happen because possibly some of the minors of the matrix A is equal to 0, right? So that's why you can really detect when you write a program for the LU factorization, you can detect right away if there's something wrong or if there exists no LU factorization for your matrix. Okay. So if you want to write the program for the crowd factorization, so you can just make use of theorem 7.10 and 7.11. Do this in a for loop, right? So this should be one for loop because they are kind of independent of each other. After you get L11, you can compute for all the U1Js. And then after the for loop here, another for loop for the iterative process of getting all the columns of the matrix L and all of the rows of the matrix U. But make sure you do it in this order, right? Because you need to know the nth or the kth row, or sorry, the kth column of matrix L before you'll be able to generate the entries on the kth row of the matrix U. Okay. Now, last semester, I tasked AMAT 255 students to derive a similar routine for the Doolittle factorization, but I guess you can just Google them and then you'll get the same formula. But I hope this gives you an idea or an inspiration on how to derive the programming form of Doolittle's factorization. Okay. Now let's just take a look at a particular example of how crowd factorization is employed. Okay. And then you see the striking difference between the two derivations that I employed. Doolittle's factorization was derived in such a way that in order to get the LU factorization, I need to do the Gaussian elimination process, right? Now, if I don't know any linear algebra, I could have just derived Doolittle's factorization in the similar way as what we did for crowd factorization and get a more pragmatic form for that formula. All right. Now let's see. Theorem 7.7, you'll see in this example, I don't need to know any linear algebra stuff, and I'll still be able to get the crowd factorization or an LU factorization for the matrix A. The matrix A is given this way: 1, 4, 3, 2, 7, 9, 5A, -2. And I'll assume that it has an LU factorization in Kraut's form. So I have a lower triangular matrix and a unit upper triangular matrix U. And I still don't know what the values of the entries are, except for the main diagonal of the upper triangular matrix, which are fixed to be equal to 1. Okay. Now, I can easily find the first column of the matrix L. Again, we concluded that they are just a carbon copy of the first column of the matrix A. So you can just forgo the computation, just do the assignment. So we'll be able to find this, and everything else are still unknown. But after knowing the first column of L, we can proceed to computing the first row of the matrix U. Okay. Again, to find that, I'll take advantage of this guy times this guy. So that's gonna give us what? That will give us U12, and U12 is equal to A12, so that should be equal to 4, right? So 4 goes there. And then first row times the third column, that will just leave us with U13 equal to 3. So that goes there. So again, I think the process, the pattern is also clear here. The first row of the matrix U is also the first row of the matrix. Will that always be the case? Oh no, sorry, it won't be the case always, because again, I am dividing by L11. Just so happened here that L11 is equal to 1, so it appears that the first row of the matrix U will be a carbon copy of the first row of the matrix A. But that's not always the case. I was too excited about the pattern, but you look at U1J, it's AIJ, right? The entries on the first row of the matrix A divided by L11. Actually, I think there's a typo here. It should be A1J. Okay. So that's A1J over L11. Okay. And with that, you'll be able to determine this. Okay. And then now to get the entries of the second column of A, so I'll proceed by multiplying this guy by this guy. So I'll get this product 8 plus L22, but that will be equal to second row, second column. So this should be equal to 7, right? So 7 there. So L22 will be equal to -1 over there, right? So we'll be able to find L22. So this is okay. And then I'll multiply third row by the second column. That will give us 20 plus L32 equals A32, right? But A32 is 8, so we'll have 20 plus L32 equals 8. So L32 equals -12, right? So that's -12, right? So this will also be known, okay? And then after you know the entries here, the next step is to know U23, right? But U23 can be found by multiplying the second row, this guy, by this guy, right? So we'll get 6 plus L22 U23 should be equal to A23. A23 is equal to 9. So we'll have 6 plus, do we know L22? Yes, L22 is -1 times U23. You do the arithmetic, you will get -3. Okay, so this is also known. So the last step is to find L33, but that's fine. So to get the third column, the third column of L, you multiply this guy by this guy, right? And doing so will give us -53. And that will give you the Kraut factorization or the Kraut LU factorization of the matrix A. Okay. So from these two illustrations, now you know Doolittle's factorization, you know the Kraut factorization. Which do you think is easier or more efficient? Kraut or Doolittle? Or you can't decide yet? Okay, so I'll let you sleep on it first, right? So I think that's the end of this particular module. Okay, now the question is, do you want to go have a problem set or an exercise set right now at this particular point? Of course, you don't want to get a problem set, right? But I'll probably give you 3 problem sets for the course, right? And one of them will be about matrices, right? So we still have how many? I think we still have 3 topics for matrices. We have QR factorization, and we have the Moore-Penrose pseudo inverse. So I need to have one problem set from those 3 topics. So I know that you already have a deadline from Dean Jomar for March 30. Is that right? Is that what Jihan said? Yeah. Yeah. So do you want me to add that at this point, or you want to focus on that first and then I'll give you a problem set next week?
Yes, okay. Can we focus on that first, then next week give her a problem set?
Sorry, Clarence, I didn't get that. Can you repeat?
Please, sir, can you please go on with the problem set? Your focus on the first problem set, and next week you can give us the problem set.
Okay, yeah, that's fine. Yeah, Peter.
Okay.
Hello.
I think since the semester is on, and then for me, my fear is the aspect of the three problem sets, being part on us at the end of the semester or a certain point in the semester. So maybe I would suggest that you just give your problem set, the first one, not everything now, at least the first one. You can work on that, and because uh, Prof. Joma's assignment is a research work, and that needs to be done bit by bit and everything. So I think we can just get your problem set, because Prof. Joma problem set, his research work ends the end of this month. So when we get in your problem set at the end of this month, it might be like jamming, with other problem set that you make it. So yeah,
Uh-huh.
I might suggest, if it meets the body, that just give us the first problem set.
Mm-hmm. Okay, yeah. Yeah, let me think about that for a moment. Probably I'll just give you two problem sets just to make things lighter for you guys. So just two problem sets. And then probably I'll give you the first problem set from me next week. So if you can try to work on the problem set given by Dean Jomer this week, all right, before I give mine next week. But the deadline for that probably would be if Dean Jomer gave you until the end of the month, probably first week of April would be the deadline for my problem set. Will that be okay? But I'll give it to you next week.
Yes, sir. Okay.
All right. So I think that's a good compromise, right? But if you are having difficulties finishing it, just let me know, right? So I can adjust the deadline. The only thing I'm trying to avoid is that all of those problem sets piling up with you at the end of the semester, because you have final exams to worry about, big requirements during the end of the semester, and I don't want our problem sets to add to your burden during the end of the semester, right? Because if I won't give you a deadline, you might procrastinate doing it. If you're like me, I'll wait until the last minute to do my problem set. So yeah, but I'll condense the problem sets so that you can probably do them in 1 week. All right. So yeah. Okay. So that's it. I'll give you the problem set on next week, and the deadline would be first week of April. I'll give you more details next time. But next time we'll talk about QR factorization and the Moore-Penrose pseudo-inverse for matrices. I have the materials already in our website. So those are the PDFs. Let me look at the title quickly. If you go to the webpage for Unit 2B, it's under under written modules on matrix factorizations. That's QR decomposition, and then under number 3, solving linear systems with singular or non-square matrix, non-square coefficient matrix. So the materials for next week would be learning materials number 1, bullet number 2, and number 3. All right. So those would be our discussion points for next week. And after that, I'll be finished with linear algebra. And when you see me next, we'll be doing actual basic data science, machine learning algorithms. So I hope you spend the next couple of weeks downloading and getting familiar with MATLAB, because I'll be using MATLAB to demonstrate classification and clustering algorithms. Okay. Any other concerns?
No, sir.
All right. So if there are none, then we call it a day. Thank you for coming today, and then enjoy the weekend, guys. And let's see each other again on Tuesday. All right. Bye, guys.
Thank you, sir.
Thank you, sir.
All right. You're all welcome.
Thank you, sir.